Hello, everyone. Welcome to UConn Online, which is one of my bedrooms in my house right now. We're super pleased to have Professor Ling from LSU with us for this series of lectures on hypergeometric functions, characteristic sums, and applications. Professor Ling, she works at LSU and has many publications, at least like 35 publications that you see in the CV, multiple grants from different sources, NSA, NSF. She was the 2012 AWM Legendre Memorial Prize awardee, and she's just a worldwide expert on the topic of hypergeometric functions. So we're very lucky to have you today with us, and here we go. Take it away.
All right, thank you. I would like to thank everyone for being here, and I really appreciate the opportunity, which is actually kind of making me to look back several papers that we have done in the past. I think starting a little bit more than 10 years. The first one was produced when I was pregnant with my younger daughter. And then I'm very super lucky to be able to collaborate with a lot of collaborators, especially my colleague Fanting too, that we have been, she opens the door to me for character sums. So she's also kind of working together with me on the lecture notes. The first one, I mean, it's still very primitive, but this is the hope. We are hoping to reach out to more people. The first part is kind of currently available in a very primitive form. So let me get started. So I'm going to try out, so you can see my screen. And the plan for the 4 talks will be, today I'm going to talk about the classical setting. All right, so this is based on many known results. So basically we'll be hypergeometric functions and differential equations. And then I will get to hypergeometric formulas and one very particular example called the Legendre curves, which is kind of wrapped around many different topics I would like to talk about during the 4 lectures. Tomorrow, I'm going to spend time on finite field versions of hypergeometric functions and including point counts on very particular kind of varieties. And the third day will be Galois perspective and Galois representations. And the fourth day will be more on the p-adic aspects and supercongruences. All right. Okay, here we go. So again, I'd like to say that the lectures aiming to reach out to people, including graduate students with some basic backgrounds on number theory. So I'm going to start with very basic notations. The first notation is called the Pochhammer symbol. It's also called the rising factorial. So if you have a number A, right, so let me try out. If you start with A over here, there's no color. Let me see. Okay, anyway, so you start with the number A, and then there's a subscript, which is actually can be any integer that you like. But if it's a non-negative integer, then the notation will be start from A, then times A plus 1, and all the way to A plus the subscript minus 1. And the convention for the subscript 0, the value will be 1. And we can write a very kind of useful formula, which is the binomial coefficient in terms of rising factorial. If you write the binomial coefficient, and then it can be expressed if you choose k elements from n elements, you can write in terms of a rising factorial on the top with a negative sign. There is a minus 1. There is a sign minus 1 to the k, and then there is k factorial down here. And now for, let me see, I'm still trying to figure out. The next gadget, which is useful, is called the gamma function. So I record the definition for gamma function here. And if you start with a complex number whose real part is bigger than 0, gamma function can be defined as an integral. So it goes from 0 to infinity. The variable that is t over here. And then there are two parts. One part, this part over here, e to the minus t, is additive in t. So this part is additive. And this part over here will be multiplicative in t. So we're going to see this feature tomorrow for when we define Gauss sum. And it's well known it satisfies the functional equation. If you compare, especially for the cases you're avoiding the poles, it's gamma x plus 1. The functional equation will be gamma of x times x to the front. And in terms of the rising factorial can be written in terms of the gamma function. So it's the gamma value a plus the subscript over gamma a. So for this definition, you can, if you like, you can extend the subscript of the rising factorial to negative integers. Now I would like to talk about two key properties in addition to the functional equation of gamma function. The first one is called the refraction formula. So if you start from a, gamma of a, for any actually positive, for any complex number, if you multiply gamma 1 minus a, what you will get to, sometimes it could be, you might get to a pole over here, but if you're avoiding the pole of gamma a, you get to pi over sine pi a. For my applications later, my a are more or less rational numbers. So what we're getting to is gamma a times gamma 1 minus a will be pi over an algebraic number, which is sine pi, a rational number. And the other formula, which is very useful and very fundamental for gamma function, is called the multiplication formula. For example, if you start from gamma a, and then you add to a phase kind of rotation 1/2. So if you do such an product, gamma a times gamma a plus 1/2, what you will get to will be double the value of a. All right, so on this hand side, you have gamma a and gamma a plus 2. And the right hand side, you double the angle to a. And plus, there are additional factors. So this factor over here, gamma pi 1/2, essentially is gamma 1/2. Right? And then there are some power of 2 because this is a double angle formula. So there's some power of 2 here. And in terms of rising factorial notation, is actually more compact. So it says if you start with a over 2, and then you do the rising factorial, and then multiply gamma. So this part over here is a over 2 plus 1/2. You do the same rising factorial. What you will get to is the rising factorial. The angle have been doubled to a, and the subscript has been doubled with the power 2 here as well. It's kind of interesting to say that actually from what I'm going to say, there is a lot of transcendental theory in the background. One of the very fundamental results is proved by Nesterenko. It says the following: if you start with any imaginary quadratic field with fundamental discriminant minus d, and then if you let this character to be minus d over, so this is going to be the corresponding Legendre symbol minus d over the input over here. Then these three numbers, the first one is pi. We have seen pi up here already for the refraction formula. The other number is e to the pi times square root d. And then the next number will be this combination. So you can make a combination of gamma values. The way you make it is you range let the numerator go between 0 to d. So you go from 1 to d minus 1. And then you put into the numerator, the denominator will be all d. And then they will go either positive or negative, depending on whether the symbol over here is going to be taking value plus minus 1. And the surprising result will be these three numbers will be algebraically independent. All right. So for instance, if you can check out the case where D is going to be 3, then immediately what you can see will be pi e to the pi square root 3, and then you have gamma of 1/3 dividing out by gamma 2/3. The three numbers will be algebraically independent. So what I want to stress will be actually in transcendental number theory, these numbers like pi and gamma functions are basic building blocks. And sometimes we would like to ask to what extent that such a result will be true, or when I can find relations among the product of gamma values, right? So that's the gamma function, which is one of the building block. The second function I'm going to talk about will be actually the beta function, which is closely relating to the gamma function. So the definition for the beta function is, suppose you start with two complex numbers, both real parts are bigger than 0, then you can define essentially the beta function, beta value for xy, in terms of also an integral. This time goes from 0 to 1. And now you're going to put together two, what I said, multiplicative functions. One, I use the input x. The other one, I use the input of 1 minus t. So I put into two multiplicative functions. The multiplicative function applying to t and 1 minus t, and put them together in such a following way. With a shift in the exponent, there is a -1 here, -1 over here. So the assumption on the real part of x and real part y, both bigger than 0, can be relaxed if we're going to do the so-called Pochhammer contour integral. So the way you do it is basically you start from 0 and 1. You look around carefully, just like the commutator. So you look around in the way, so you produce a commutator between the two loops around 0 and 1. So if you're doing the integration around such a contour parts over here, then you can get to the beta function as well. It's a very similar kind of definition. The difference is instead of using 0, 1, I'm using this particular closed loop. And in front of it, there are two explicit values. This part over here, there are 1/2 numbers. When both x and y are rational numbers, again, they are algebraic. And I forgot to say that if you have any questions, please feel free to let me know. Just voice out, because I don't know the system very well. So do not send me kind of private messages. I won't be able to check it right now through the chat box. Okay. And now let's start with, so with the basic players, one called the gamma function, one called the beta function, we're going to check into the hypergeometric parameters. So here, when I say alpha, it's going to be a multi-set, consists of alpha consists of A1, A2, all the way to Sm over here. They are rational numbers for this lecture. And the elements can repeat. For instance, I can do 1/2, 1, 1/2 again. So the order for right now, for most of the cases, do not matter. And given such a multi-set, it's said to be defined over Q if I'm going to use the rational numbers to make root of unities. And then I'm going to use a formal variable x, and then take x, subtracting those root of unities, and then multiply them together. A priori, I get a polynomial with coefficient in a few of cyclotomic numbers. But in case the numbers turns out to be integers, then we say that the multi-set is defined over Q. And another notation which will be useful for later is when it's called self-dual. So self-dual notion will be, if we have alpha, minus alpha will be I'm going to negate all the numbers. in the alpha set. If after negation they are the same modulo z, then the alpha set is said to be defined over z. So for instance, if I'm going to write down 1/3, 2/3, so this is a multi-set consists of two rational numbers. And if I'm going to check this particular kind of polynomial, we get to x minus cubic root of unity, and then x minus cubic root of unity square. So we have x squared plus x plus 1. So this checking that this particular multi-set is defined over Q. So it's defined over Q, and of course it's also self-due. And if I change it slightly to 1/3, 1/3, then both conditions will be violated because the negation is going to be different from 1/3 and 1/3, even though modulo z. All right, so this one is not. Okay. And when we talk about a hypergeometric parameter, it's going to consist of two such multi-sets. One I call alpha for this lecture series, another one is called beta. So they all consist of rational numbers, and also the convention over here. And I'm going to set the first one in beta, B1, is fixed to be 1 for B1. And such a pair, so another feature about those pairs will be they have the same kind of cardinality, which is also kind of, this is the agreement for the setup for my lectures. And such a pair is called primitive if the difference between AI and BJ, for any I and J, the difference is not integers. Otherwise, it's in primitive. Another notation will make my life easier will be I let the capital letter M over here for most cases, if no ambiguity, will be the least common denominators of those AI and BJ elements. For instance, if I have my 1/3, 2/3 as above, this is my alpha, my beta, say if I say it to be 1 and 1/2, then both of them are defined over Q, which is easy to check. And the LCD over here, which is denoted by the capital letter M, is going to be 6. It's the least positive common denominators of both alpha and beta. Okay, now definition for hypergeometric functions, the first introduction will be it's a formal power series. So it's written in the way, and the compact notation for me will be I simply write as f hypergeometric function with alpha beta multi parameter set. Z is an argument over here, and this is the classical notation. And so the alpha goes like upper parameters, and the beta, including 1 down here, will be the lower ones. So it's a formal power series of z, goes from 0 to infinity. And so the coefficients is going to be computed by using the rising or the Pochhammer symbols. You're going to use A1, A2 on the top to build for the k when it ranges in this range over here, the rising factorial, going to multiply them together. And then you're going to do the same thing for the denominator. In particular, for B1, which is 1k, it's nothing but 1 times 2 all the way to k, so it's k factorial. Right. So this is the definition for hypergeometric functions if I'm referring to alpha, beta, and z. So it's going to be a function. It's a formal power series. Okay. And now, let me quickly go into how you get to those functions kind of inductively first, before I get to the defining differential equation or the differential equation to satisfy. So this is actually the notion we brought out in 2014 with Jenny Fuselier Ravi Ramakrishna and Holly Swisher and something too. So we call them period functions because of what I'm going to tell you is the Euler integral formula in the next page. So we call the period functions to be the functions that we define inductively. So we start from the first one, which is 1p0. And the way we defined it, it's actually A1, which is the first entry of my multi-set. And then here hidden, it will be 1, which is for the B1. It's defined to be the formal power series 1 minus z to the minus A1 power. So you can expand it using binomial coefficients. Then you can inductively build the next kind of period function from the previous one inductively from the following manner. First, you chop off the first part of your period function, you put it down here, and then you use the same z, and then you put an additional variable t. You let the variable t go from 0 to 1 if there are assumptions on the values of a and am plus 1, bn plus 1. Otherwise, use contour integral as what I mentioned. And on top of the inner layer, so this is the inner layer of the period function, you put t raised to a power very much similar to the construction. For the second one, is similar to the one down here. And so you use the last two numbers in the way that you're going to arrange them in the following order. For instance, if I use this inductive formula to look at 2p1. So for 2p1, there are a1, a2, and then b2 down here. By definition, basically, it's going to be the integral from 0 to 1, then x raised to t is the same as the dummy variable x raised to a2 minus 1, 1 minus x, b2 minus a2 minus 1, and 1 minus zx to the minus a1, which is the p1, 1p0 function. Okay. And now let's see how the period function is related to the hypergeometric function that I introduced using formal power series. So if we're going to kind of expand out 1 minus zx using binomial coefficient, so this is the standard computation over here, and minus a makes my life a little bit easier. I don't need the sign, I don't need negate minus a over here, so it's written in the following form. And if I get to 2p1, by definition, it's integral. And the way we do is this integral, which is the idea of Euler. So what he said is now you're going to apply the binomial coefficient to this entry over here, then you get down to a formal power series expansion. Let's forget about convergency for this moment. And now, so you get to some power of, there is some rising factorial, there are some additional powers of z and x coming in. So you put out the z power up here, you let the x power go here. So what you will get here is nothing but a beta function. And beta function, I forget to say that the beta function, the important thing about a and b will be, it can be written as gamma a, gamma b, over gamma a plus b. Okay, that means I can write things in terms of the gamma function, and gamma function has functional equation, etc. So you eventually can see that these two are identically the same. So the last two are identically the same. And from the Euler integral formula, we observe something which is kind of interesting. The interesting to us is, firstly, if we start with this definition, to us it's more geometric. If I start with this definition, the role of A and B are not commutative. I cannot interchange A and B right away. If I do, kind of by brute force change A and B, I get to a different integral. However, the difference is kind of minor in the sense that their major part will be the same. The difference lies in the gamma function part. So they're actually kind of telling us when we get to the finite field version, this is the idea that there's a normalization process going on over here. Then we can try to imitate for the definition when we get to the finite field version. All right. So with that said, we get to the normalized period function. For the normalized version, so what we start with basically is also inductive formula. 1f0 will be the same as 1p0. It's 1 to the z to the minus a1. And then for the normalized period function, the only thing we will do compared to the period function defined as integrals, so it will be iterated integrals. The normalization over here is we're going to do the normalization by dividing the corresponding beta values. By doing so, we gain what? We gain firstly, the leading coefficient will be becoming 1. As we wrote down the formal power series expansion for the classical hypergeometric function, the leading coefficient is 1, which is kind of convenient later when we try to attain formula and trying to see what's the scalar. If they're different by scalar, how to compute the scalar. So it's becoming useful. And the second thing we gain over here, as what I mentioned, the period function, I cannot interchange the upper parameters or the lower parameters arbitrarily. The order matters for the definition up here, but the order does not matter for the normalized version over here, so which is actually kind of more convenient. The normalization process will kind of remove the ambiguity, how the period function depends on the orders. Okay. Any question before I move on? Okay. All right. And then let me get to the hypergeometric differential equation. The one very kind of convenient way to get to the differential equation is using, instead of the derivative, the notion, the z and lambda are the same. I noticed that. This is the theta notation. If I have a variable z, right? So instead of looking at derivative with respect to z, it's z times d dz. So if I try it out, because we're basically dealing with formal power series, and if I try it out on this notation, it's actually convenient to see that we are going to get kz to the k, all right? So that the degree will remain the same, and then the power will go to the front. And using the fact that hypergeometric differential equations are defined by rising factorials, so the coefficients are recursive. Using the property, you can easily check that this combination, all right? So I'm going to come up with the differential operator. I put the alpha and beta multi-set down here. The last one referring to which formal variable I'm using. So this combination, I take a product of my theta z plus the lower parameter minus 1, take a product of that. You can check that it's commutative in terms of polynomials of theta. And then subtracting z times product of the theta plus the upper parameters. This differential operator, of course, will have degree m over here, will annihilate your formal power. This is hypergeometric functions. So this hypergeometric function is going to be a solution of the homogeneous differential equation. All right. And
Ling,
yes?
it should be pointed out that these results don't require that your system is defined over a Q.
No, no, no.
That's right. So you could do this with any
right,
parameter,
yes.
A and B.
You
Right.
are definitely right. Bill,
Okay.
that so far, we don't need any kind of requirement on alpha, beta being defined over Q. So the definition is here. You can plug that in and get what you're going to see. But the result will be nicer when the parameters are self-dual. All right. Okay. So this is actually classical theory, so it's the content is available in many textbooks. The particular textbook we use a lot is the book called Special Functions by Askey, Andrews, and Roy. Okay. And for example, if we get to alpha beta to be this particular choices, so it will be the 2f1 cases. And the variable, if I use that, is lambda. And you can use the conversion between d, which is derivative respect to z, and then zeta z, which is z, d, z. You use the conversion between those two derivations. You can write down the normalized differential operator. The normalized means it's 1 up here. And just like this differential operator, all the hypergeometric differential equations will have only 3 singularities, which you can see for the present case that the denominator could be 0 at 0, lambda equals 0, lambda equals to 1, and also infinity. All right. And it's also called Fuchsian differential equation in the sense that actually the singularities are very mild, which allow me to compute the so-called characteristic equation at the singularities. So at the singularities could be 0, 1, or infinity. The way you compute it will be depending on what's the order. You first write down the lowering factorial. So instead of adding, you're subtracting. All right, you use the r, which is now a formal variable. You applying the Pochhammer symbol in the opposite way. And this is the degree of the differential equation. And then you do it in the way that the lowering factorial in the decreasing order, there are constants. The constants are computed by using the corresponding kind of the coefficients. Say for the i's coefficients computed as, the last one is computed as x minus the singularity raised to the degree, which will remove the pole. If it's Fuchsian, then you evaluate s equals to a. So let me give you an example over here. So if I'm looking at this differential equation, let me erase so that you can see that better. And if I'm trying to do this computation at lambda equals to a, which is 0, say for instance, if I want to compute the corresponding characteristic equation, the way I do it is I know that the order is going to be 2. The first term over here is nothing but r times r minus 1. The second coefficient, if I want to compute the coefficient, I'm going to look at this term over here. And the recipe will be, I'm going to multiply with lambda. And so I get rid of this lambda in the denominator. Then I slash or plug lambda to be 0 into here. And it doesn't matter anymore for the second term. So the only thing remaining will be b2 over 1. So it's b2. And then continue the next term over here. I'm going to do lambda square and evaluate at 0. I get 0. So this is the characteristic point equation for this degree 2 differential equation at lambda equals 0, which is a singularity. So for this one, if I reorder it, I can write it as r plus b2 minus 1 times r equals to 0. There are 2 solutions. One solution will be 0. The other solution will be 1 minus b2. So will be 2 local exponents. All right, so that you compute it, which is relating to the local monodromy I'm going to mention later, the Jordan from. Okay. And now you can compute for all the singularities in the very explicit way. But it's already known that if you have such a differential, hypergeometric differential equation as lambda equals 0, the local exponents, the characteristic exponents are 0, 1 minus b2, as what I attained in the previous example, 1 minus b3, etc. At singularity infinity, the exponents are a1, a2, all the way to am. And lambda equals to 1 is actually a very interesting point. So the local exponents turns out to be 0, 1, 2, all the way to a minus 2. And the last one is called gamma. Gamma can be computed by -1 plus the lower parameter sum minus the upper parameter sum. All right. So if we get back to the example for the 2f1, so we get to the what we call the Riemann scheme. You have singularity 0, infinity, and 1. The Riemann scheme kind of recall down here the singularities, local exponents. For 0, I compute as 0 and 1 minus b2. And then this formula tells you that at infinity is going to be a1, a2. And it also tells you at 1 is going to be 0. And the other value is -1 plus 1 plus b2 minus a1 minus a2. So -1 and 1 compromise. So it's b2 minus a1 minus a2 here. All right, so it's called the Riemann scheme for 2f1 hypergeometric differential equation. It's actually kind of useful, which is the local exponent for the hypergeometric differential equation basically will determine the whole system. All right. So let me also spend kind of maybe 1 more minutes on the cases at 1. All right. So the local, the local monodromic, okay, which is actually when I get to, so that means actually there is a matrix corresponding to the behavior of lambda equals to 1. I'm going to get into that. But the important thing from over here, which is originating in Pochhammer's kind of results, is actually telling us that near lambda equals to 1, the local matrix is called Cauchy refraction. I'm going to come back to this notion later. The important thing will be the local monodromic matrix take away, the identity matrix with the same rank. The surprising thing is the rank is only 1. All right, so this is actually the notion of Cauchy refraction. It will be relating to some behavior when I get to the representation, Galois representation, when I specialize lambda equals to 1 later. Right. So the rigidity theorem says that if you have an ordinary differential equation, which is Fuchsian, and has only 3 singularities, 0, 1, and infinity, then the local exponents basically essentially completely determine your differential equation. If they turns out to be this form over here, then your differential equation after normalization means the leading coefficient to be 1 will be the same as what we're going to write down. Right? So it's going to be called the rigidity theorem. It's very useful for attaining identities. And then my colleagues, Fontaine and Bill Hoffman and Fontaine actually use this idea, attain identities over finite fields as well. And let me also talk about local solutions, right? So actually what I'm trying to tell you is everything will be very explicit, very computable, highly computable. So this is a standard kind of results in ordinary differential equation. Now we have a differential equation, which is order, the degree or the order is going to be the same as the length of the parameter set alpha. So the solution space at ordinary points will be n-dimensional. Right? Typically, you can compute solutions by using the Frobenius method. And for example, near singularity z to be 0 over here, and when b2 is not an integer, so the local kind of exponent, as what we said, is 0 and 1 minus b2. They will be different. In terms of local monodromy, the Jordan form is diagonalizable. which allow you to essentially write down two very distinct solutions. The first one is what we actually starting with. We actually telling you that this hypergeometric function satisfying the differential equation. The second one you can also write down. It's also holomorphic near zero. So it starts with a term over here telling you the correct local exponent 1 minus b2. And then you can also put down all the terms in the way. You can check the local kind of characteristic exponents, they will be the same. There are two different solutions because the leading term over here is 1. The leading term down here is z to the 1 minus b2. There are two very different solutions. So there are basically two different eigenfunctions near 0. And if b2 is 0, it's an integer, say b2 is 1, the situation gets a bit more complicated. The second solution is going to be a log nature. So it's log times the first solution. And then there is another kind of very explicit formal power series you can write down involving, which is basically this sum over here is what we call the partial harmonic sum, or sums of that nature over here. I want to tell you that everything is very explicit. It depends on the local monodromic matrix, the nature of that. And it's easier to work with the holomorphic ones, but in the end, it doesn't quite matter. Everything can be put into very concrete kind of settings. So let me get to the monodromy representation. So what I'm having telling you is now with a given Fuchsian differential equation, you know the local system, all right? So if this is a CP1, you know the singularities occurs to 0, 1, and infinity. And now if you're going to look at CP1, all right, I should probably join a sphere over here. Removing 3 points. So what we get to is a ball with 3 points removed. So you can compute the corresponding fundamental group. So it has basically 2 generators, the loops around 2 of the singularities. And the so-called monodromy representation, the idea is follows. You pick a smooth, a regular point at 0. And then you know that above this regular point, the solution space is going to be a vector space. So it's going to be a vector space. So you can write down a basis very explicitly. Then what we're going to do is, now if I have a loop on the fundamental group of the CP1 removing 3 points, then I can go around the punch sphere any way I like. And if I make it into a continuous function, I can actually expand the solution, the local solution space. I write down a basis. If I call F1 all the way to Fm, they're linearly independent. If I'm going to do it analytically, extending the solution set along my loop, when I come back, I'm going to get to another basis. They are still linearly independent. So I can write in terms of the original basis, multiply a matrix. The matrix will be lies in GLMC. So this matrix only depends on the class, the homotopy class of my loop in the fundamental group. So if I start with a homotopy class, I'm going to get a matrix. This is a homomorphism. And so this is a homomorphism sending the fundamental group of CP1, the base space, removing singularities at any regular point, you get to a group in GLMC, which is called the monodromy group. And it's kind of unique up to conjugation by GLMC. And so it's called a monodromy representation of L. When I get to the notion of local monodromy matrices, that means when I'm wrapping around 0, 1, infinity, say 1 here, and then I look at the corresponding matrix. Right. And then what's the nature of the characteristic exponent? The nature of the characteristic exponent will be, say, if I'm looping around 0, I get this matrix M, L0, and I can compute the Jordan from or the eigenvalues. The two eigenvalues, one will be e to the 2 pi I times 0. The other one will be e to the 2 pi I 1 minus b2. So the eigenvalues, the characteristic exponents will be relating to the Jordan form over here. Say for near 0, it's e to the 2 pi I 0, e to the 2 pi I or 1 minus b2, when the case we are looking at is n equals to 2. Okay, any questions? I will need a drink. All right, okay, no more questions. I mean, if no question, then let me continue. There is an explicit way. This is a very important result of Beukers and Hamme, which actually tells you that for primitive, under the primitive assumption, if you get to alpha and beta, all right, so they can do it a bit more arbitrary, but I fix my beta to start with 1. All right. There is an explicit way to determine the corresponding monodromy group. Basically, will be the image of the fundamental group under a monodromy representation, as well as its Zariski closure into GLMC. All right. So I only want to mention that there are a few possibilities. The first possibility is the image could be finite. All right. So let me get to one special case down here. So it could be finite. If the image is infinite group, then there are also cases if alpha beta are self-due, and then you compute C, which is e to the 2 pi I gamma. Gamma is the special exponent at 1, which is -1 plus sum of the lower parameter take away upper parameter. If it turns out to be 1, self-due plus C to be 1, then they know the Zariski closure will be SPM. And if it's -1, then they know the answer will be the orthogonal group. Otherwise, they have this conclusion over here. The special linear group will be inside the Zariski closure. And the one very kind of relevant description for our cases will be if alpha beta, all right, now I'm going to specialize so that just the description will be a little bit easier. If alpha beta define over Q, both of them define over Q, then the finite monodromy is actually correlate to what they describe to be interlaced behavior. That means if you look at e to the 2 pi I aj, so you get root of unity, and then you have another root of unity, another set of root of unities coming from the beta set. If on the root of unity, they interlace. That means you have one alpha, then you get to another beta, another alpha, another beta. Then you know that the image of the monodromy group will be finite. So let me get to examples here. All right. So there are two examples. One, the alpha set consists of 1/2 1656. It's easy to check it's defined over Q. Similarly, if I take beta to be 1, 1/3, 2/3, it's also easy to check that it's defined over Q as well. For this parameter set, if I plot the corresponding root of unities, I will start with the first one. If I start from here, it will be from the beta set, which is red. The next one going around in the counterclockwise, I will get to e to the 2 pi I times 1/6. So we'll be on the alpha set, and then from the beta set, from the alpha set, from the beta set, from the alpha set, from the beta set. So it's called the interlacing. All right. So for this particular case, it's true that the corresponding kind of the image of the monodromy group will be finite. For the second case, if I just kind of replace 1/3, 2/3, or swap the row of 1/3, 2/3, and 1656, the situation is now different. Again, start from 1. It's coming from the beta set. And then 1/6 is also from the beta set. Then the alpha set all go this direction and the beta set again. So it's no more interlacing. For this case, the corresponding monodromy group is going to be the Zariski closure is the orthogonal group of O3C. Okay. Any question? Okay. Okay. Let me get to the Schwarz theorem. Maybe it's time to take a break first.
Yeah, so I'll stop the recording here.